Next we come to least mean square equalizer. An automatic equalizer with self-adjusting taps is required in many scenarios when the channel state information is not known. Even when it is known, it eventually changes with time. To understand the intuition behind the LMS equalizer, assume that you are on a holiday in a nice theme park and you are riding on a roller coaster. Sitting on the front seat, you have access to a hypothetical set of brakes and there is no anti-rollback mechanism. Suppose that the electricity goes out. To prevent the rapid drop, a good strategy is to apply the brakes and then leave the brake so that the roller coaster travels in a direction opposite to the gradient. And then we apply the brakes and then leave them again. And then we apply the brakes and then we leave them again. The roller coaster will slowly descend in the direction opposite to the gradient and will come to rest at this optimal point. Similarly, a quadratic function is a very similar performance function, which is given for one tap. Here we can see the gradient and we want to travel opposite to the gradient in a slow manner by applying a set of brakes and leaving them such that we eventually come to rest at this point. For a two tap equalizer, this performance function is given by a shape like this. It is difficult to imagine this for more number of taps. It turns out that the eventual update equations are given by Z is the match filter output, the input to the equalizer. EM is the error between the equalizer output and a training sequence where the data symbols are already known. When the data sequence is not known, a decision directed approach can also be applied. Mu is that hypothetical set of brakes we discussed in this slide, which is a very small constant that helps in avoiding large deviations from the previous step values. We call it a step size. An LMS equalizer usually operates in two stages, a training stage and a decision directed stage. In training stage, the training sequence AM is known, which is used to compute this error, AM minus YM. In the decision directed stage, when the equalizer has converged, Ym is sliced to estimate A hat M, which is then used to compute the subsequent error. Here is an example of an LMS equalizer. We are using 4 core with excess bandwidth alpha equals 0.25. The channel response is given by these taps and there are 3 different step sizes, mu equals 0.01, 0.04 and 0.1. As we can expect, largest mu has the fastest convergence while the smallest mu results in a slower convergence. However, this is not the complete story. Remember from the roller coaster analogy that if the brakes are not properly applied and it is thrown towards the equilibrium point too quickly, it can flip over in any direction. When the equalizer converges to this optimal solution, the taps do not stay there, but they keep fluctuating. With a large step size, the excess error is larger as compared to a small step size after convergence. This is a dynamic scatter plot where we can see the convergence of the modulation symbols towards their actual values, and we can see that the effect of channel is gradually reducing with time. Let us take a GNU radio example. In GNU radio, LMS DD equalizer block implements a decision directed equalizer where the gain is the step size mu we have just discussed. Number of taps in the equalizer, number of samples per symbol can be either 1 for symbol space equalizer or usually 2 for a fractionally spaced equalizer. Constellation is the final constellation of the transmit signal. In this example, we have a step size mu of 0.01, 11 taps and a QPSK modulation and a symbol space equalizer. We can see that the input to the equalizer is all over the place, although we can still spot a structure in the receive signal. The spectrum is given here. After the compensation with the equalizer, the spectrum at the equalizer output is ideally flat.
Since it is not possible to implement feedback loops in GNU Radio Companion, I have made this flow graph to see the working of the LMS decision directed equalizer. Later, we will go to the code of this block and we will see that this is pretty simple and it is very easy to write a code for such a kind of a equalizer. Let us start with the variables. So I have a GUI chooser that chooses among 3 channels, channel A, channel B and channel C. These are the standard multipath channels discussed in Prakis book. Prakis has written an excellent book on digital communication. So the variables contain the coefficients of those multipath channels. Later we will see that channel A is pretty benign, channel B is relatively harsh, and channel C is quite harsh. And we will see how the equalizer overcomes the distortion caused by these channels. Equalizer gain is adjusted by the slider here. The excess bandwidth is zero point 0.5, sample rate is 32,000, and there are two samples per symbol. I have defined a constellation object because this is given as an input to the block which defines a QPSK constellation. After the bits generation, we have the custom QAM waveform which generates the waveform at baseband. The channel model has the only distortion as the multipath channel, where this is coming from here. This input is given to the LMS decision directed equalizer after observing the oscilloscope, the spectrum analyzer, and the scatter plot of the input signal so that it can be compared to the respective outputs. Equalizer gain, the number of taps I've chosen is 13, and their samples per symbol is 2. This is input samples per symbol. The output samples per symbol of the equalizer is on the constellation object. So the output would be 1 sample per symbol. This is the Gaussian noise source with a flat power spectral density. We have included it here so that we can check the spectral response of the respective channel model. A constant number multiplied by a function would generate the same function so that we can actually see the generated spectrum and the channel spectrum on the same frequency sync. Let us run the flow graph now. And here we will see that there are 3 channel spectra. This is our transmit spectrum, which is a root raised cosine shaped QPSK waveform. And channel A, as you see, is pretty much flatter in this region. There is slight distortion, but more or less it is not much harmful. Although we do not expect that it will let the signal pass through undistorted, as you can see that the equalized signal is nowhere resembles the ones and zeros, and the equalized constellation is also all over the place. Let us change it to channel B, and you can see that channel B is relatively harsh and it shapes the waveform, our QAM waveform, within the signal bandwidth. Let's check the output, and as discussed in the lecture, in the receive constellation we have distinguished points. This represents a multipath channel, the copies arriving through the multipath. And if we look at channel C, then it actively creates nulls within the signal bandwidth. This is the harshest channel among these 3, and that's why you can see that it seems to be quite a difficult job to overcome this kind of distortion. However, once we start with an equalizer gain, we will see that the equalized spectrum is relatively flat. The received spectrum is given by the product of these two. That's why this is the received spectrum in this case. In the case of channel B, the received spectrum is visibly distorted, and in case of channel C, it is quite distorted. We start with channel A and we give a value of 0.003 to the equalizer gain, and the received spectrum you see is different than the equalized spectrum. This looks like a 16 QAM constellation, but we know that it should have been a QPSK constellation. That means we need to play with the equalizer gain and see if it is able to converge. Here we can see that it has been able to converge to decision points, and then we can slowly reduce the gain so that mean square error can be reduced. The main thing is that the equalized spectrum is now flat. At 1 sample per symbol, at the receiver we should have a flat spectrum. The received spectrum is distorted, but the equalizer has clearly converged to the proper solution. It's also visible from the waveform where we can see the clear ones and minus ones at one sample per symbol. There are two questions at this stage. Number one, how was the equalizer able to overcome such harsh channels? Number two, what happened if the channel would be slightly changing? Both of these questions can be answered if we look at the code of this LMS directed equalizer. Here on the GNU Radio website, at the C code implementation of the LMS equalizer, again, once we pass through the housekeeping stuff, we will see that the main equalizer operations are performed here, where the error signal is generated by decision minus the output of the equalizer. And the tabs are updated, update tab function. And the new tab equals previous tab plus mu, which was the equalizer gain, multiplied by error times the input conjugate. So this is exactly we discussed in the equation of the lecture. Once we go through this procedure, not only that the equalizer can overcome difficult channels, but it can also track slowly changing channels because of the updates happening adaptively in this manner.